first part of this problem, I managed to teach you how to handle when there is the velocity in the flow, and we learned that the flow would have different pressure and different temperature, that both of them contain what the velocity, the energy that velocity has. So our pressure for point, say, 2 was P2 equals 54.1 kilopascal, and then T2 was 280 K, and therefore the point 2 was a point that had no velocity, but it had a pressure and temperature which had the velocity energy inside it. That's the technique that, if you want to learn more about it, you need to go to the compressible flow part and see how do we handle total properties there. But so far so good. What we do now is to go to the gas generator part and start calculating this gas generator, which contains this compressor, and then the combustion chamber, and finally the turbine. And these three together comprise the gas generator. So let's start with the compressor, and we are told that the compressor pressure ratio is 12. So T3 would be T2 times P3 over P2, which is the compressor pressure ratio, to the power gamma minus 1 over gamma. And putting numbers to it, this would equal T2, which is 280, times P3 to P2, which is 12, and to the power 0.286. And the outcome for T3 is 569.9 K. And just to have a number for P3 equals P2 times 12, and P2 we know it to be 54.1, so it is 54.1 times 12, and therefore P3 is 649.2 kilopascal. And these are the values for P3 and T3. Once we know our values for P3 and T3, so we know all our properties for both sides of the compressor, and therefore we can calculate compressor work. And we would write it here as compressor work, which is W sub C, and that would be CP0 times T2 minus T3. And putting numbers to this equation, this WC equals 1.0045 times 280 minus 569.9, and the outcome is minus, of course it should be minus since we in fact do work on the compressor, is minus 291.2 kilojoule per kilogram. graph. And that's how we have calculated. We now have all knowledge for our compressor. Of course, our compressor is ideal compressor. If there was some efficiency for it, then we could easily calculate final properties for that efficiency. But for the time being, our compressor is ideal, and now we know everything about the compressor. We move to the combustion chamber. Well, for the combustion chamber, for the inlet conditions of the combustion chamber, we know everything, because since we have calculated compressor exit conditions, and therefore the inlet conditions for the combustion chamber are known. The exit conditions of the combustion chamber are also known, since we know that P4 equals P3, and that equals 649.2 kilopascal. And also the problem has told us that T4 equals 1100 Kelvin. That's the metallurgical limit of the blades of the turbine. So with this knowledge, where we know both the inlet and outlet conditions, the first law for the combustion chamber would tell us that Q equals Cp0 times T4 minus T3. We have everything for it, so this equals 1.0045 times 1100 and minus 569.9. And the outcome for Q is 532.5 kilojoule per kilogram. And that's all we need for the combustion chamber. Finally, we move on to the turbine, and before we start calculating turbine just like compressor, there are 2 points which we have to clarify. First, this turbine is connected to the compressor through a shaft, and whatever work that this turbine produces is used by the compressor, or better to say, whatever work that the compressor needs is provided by the turbine. So it's fair to say that turbine work is equal minus compressor work. Why is minus? Since one is giving work and one is taking work, so they should have opposite sign, and therefore this would equal 291.2 kilojoule per kilogram, and that's the work by the turbine. The second point that we should need to talk about for the turbine is that the flow that goes through the turbine is not air, but it's combustion products. Sometimes in the ideal cycle, they are assumed to be air, and air is calculated. But a better approximation is to consider combustion products. How do we do that? Combustion products, we know that gamma equals 1.333. It's possible to calculate this through gas mixture lessons that is given in another chapter of thermodynamics. But as it is for the time being, this is a good value to assume, and it's commonly accepted that this is a good value. And since Cp0 equals gamma r divided by gamma minus 1, therefore this would Cp0 would be 1.147 kilojoules per kilogram Kelvin. And so we would not use 1.0045 for Cp0, but we would use a different value, and this would give us a more realistic result for our turbine calculation. Now we know turbine initial conditions, we know turbine work, and what we need to calculate is turbine exit conditions, temperature and pressure. So what we do is we write the first law of thermodynamics for the turbine, and that is W sub T equals Cp0 times T4 minus T5, T4 minus T5. Please note this figure that I have here, and T4 minus T5 is just the difference between these two temperatures. Therefore, this would equal 1.147 times 1100 minus T5, and the outcome equals turbine work, which is 291.2 kilojoule per kilogram. And calculating this equation would give us T5 equals 846.1 Kelvin, and that is T5. Once we know T5, and since we know that the process in the turbine is isentropic between 4 and 5, therefore we can easily write the isentropic equation, and P5 would equal P4 times T5 over T4 to the power gamma over gamma minus 1, and putting numbers to this equation, this would be 649.2 times 846.1 divided by 1100 to the power 4, and therefore P5 will equal 227.2 kilo Pascal. And therefore we have both pressure and temperature at the turbine exit at this point. And you see the key with the gas generator, and the name of it is just this, that the turbine has provided all the work that the compressor needed, and there's still gas with availability, with pressure and temperature not equal ambient, with availability. And now this gas, this hot gas, may be used to get work or increase speed, and with it we can use it to run our turbojet engine. And that's what I shall do in the next video. Thanks for watching, and cheers. See you in the next video.